Thank you so much for my 30 plus subscribers. I'm so proud of it. I know this number is small, right? And people have millions of subscribers. But the fact when I started this, I wasn't imagining even 10 subscribers, right? I don't know what's going on with the social media algorithm recently. It's just not favoring me. And thank you so much. So as you can see from the title, we're about to discuss something very important in our series of understanding the system. And we're going to talk about databases, right? Data in general nowadays is the gold mine, right? Of the 21st century. It's the gold mine. It's the most important thing when it comes to applications, right? And to put this into perspective, when a malicious user go after a company, right? What they're going to do with the code? Like for example, if they targeted Facebook, for example, and they got the source code of Facebook, what are they going to do with it, right? Not much, right? Not much, because there is so much knowledge. It's not an asset for you. It's asset only for who? For Facebook, for the company, because they have the knowledge base, they have the people. But for you, it's nothing, right? It's nothing. It's valueless. So when someone, a malicious user, as we see in the news and read online, when they target a specific entity, what they go for? They go for the data. And that's why securing databases, using the right database, and understanding databases, that's the whole purpose of the series. It's not superficial stuff, right? We go down the rabbit hole as we explained. We have here Docker desktop. Let's just put like this, right? We go deep the rabbit hole, and that's very valuable for you. Why? Here is the interview tip, because when you interview for a job, especially in software engineering, I've noticed this because I interviewed with so many companies across my, let's say, humble 7 years of experience. I've noticed that if you answered one question deeply, that will leave a mark, right? It's just human psychology. The interviewer, you might mess up in so many questions, but if you got one question right and made it as a conversation between you and the interviewer, I assure you, you're going to the next stage. He's going to recommend you. Why? Because most likely a lot of people are nervous and they don't go, how to say, in more details because they're afraid to mess up. So when you go in the interview and you're asked about something that you're going to share, please go deep into it, right? Go do your own reading, because here, okay, we're going to explain stuff deeply, but we're going to leave stuff out because of time, right? And that was a long introduction. I just wanted to let you know I'm fine, I'm okay. Just life happens. And yeah, we have another video. It's called databases. And before we go into the video of databases, let's just recap on what we did so far in the series very quickly. So the first video we uploaded is about scaling your code, right? Writing scalable code. And what we meant by that, I showed you there is level into it, right? Anyone can learn how to program nowadays, right? For me personally, anyone can write a Hello World program. It's a programmer, right? He's a programmer, right? And now he starts to go level, how far he can go, right? As his code works, right? When you give him a task, does the code works? That's maybe a junior or inter level, right? And now we will go to a mid-level engineer. Is his code maintainable? Do I need to do gymnastics, just go on a mental workout just to read their code, right? And from mid-level to let's say the other levels like staff, principal engineer, what's the problem that code solved, right? How did they solve it? Is it the most optimized way? Is it the most performance, scalable way, right? Because that's how you classify engineers, right? Yes, it's about the code, but in certain different ways, and every way lead to the next level, right? And the first video is to help you understand those levels and hopefully level up your career. And the second one is basically, we talked about authentication. Authentication is very important, right? Authentication authorization, right? It's the first layer of security for your software, right? and you need to understand that well. We talked about OAuth, and we talked about authentication methods and so on. And the third video we talked about OSI layers, right? Maybe some software engineers think like, wow, this is very theoretical. I learned that in my computer science degree or in my boot camp. Yeah, you learn it, but not in the way we explain it. We explain it very deeply, right? And if you watch this video about the OSI layer, I'm going to ask you a very important question that I got asked. You see, that's how you gauge the level of the company you are interviewing with. Basically, the question that they ask you. So one company that's very respectful, the interviewer asked me this question: what's the difference between layer 4 and layer 7 load balancing? Do you know? You might say like, how is that related to OSI model? Well, the OSI model is 7 layers. We have 4 layer, right? I believe it was the network layer, if I was not wrong. And the 7th layer, you need to refresh, right? Keep the information fresh in your mind. And so layer 7 is the application layer. So I answered that question correctly. Why? Because I do review regularly, right? I do keep my information fresh in my mind. That's very important for you as a software engineer, to keep information fresh in your mind. Because I promise you, one job, right, can be very transformative for you. And yeah, so make sure you, every single time in your career, you pick the right job, the right people, ask people who worked with that people on LinkedIn, for example, and so on. So yeah, so what is the difference between layer 7 and layer 4 load balancing? Well, layer 7 is, we said, what is the application layer. So there, what do we need to do? Like, okay, we need to do load balancing, but also there is going to be a lot of filtering of the requests, right? There's a lot of things we need to process of the request, right? And that's the whole difference between layer 7 and layer 4 load balancing. And layer 4 load balancing, we're aiming for performance. We're aiming for performance and speed, right? And we don't need much filtering of processing of requests. And for example, to put this into perspective for you as a software engineer, a layer 7 load balancing is like Nginx, for example, right? Apache, and so on. And Nginx is like web server, reverse proxy, and so on. Maybe it's another topic. Load balancing by itself is a very huge topic, but I'm just giving you a recap and a review. Okay, that's a bit long, but I think it was very necessary. Now let's just jump into our topic today, databases. So first things first, what is a database? Well, database is a structured system for storing and retrieving, managing and modifying data, right? And we have 2 types of them. The first type is the relational databases, like Postgres and MySQL. And in this relational databases, we're going to have tables, rows, and schema. If you look right here, as you can see, we have rows, tables, and schema, and fields, and so on. So tables is the entity that we store our data in, right? A schema is how we describe those entities and how they interact. And row is a record, right? Is a record for each data that we insert inside the table, right? And to do that, what we're going to use, what? A structured query language, SQL. And we have a simple query here, from inventory where status in AD. That's what's going to do. Basically, it's going to return all the rows that have status in A or D, right? Great. So now the second type is non-relational databases like MongoDB and Redis. And here we're aiming for flexible schema, right? And it's very different than relational databases. And in fact, there is so many types of non-relational databases. Each one of them solve different problem. We have graph databases, we have columnar databases, we have document-based databases, and we have key-value databases. MongoDB is document-based, right? Database, and Redis is what is key-value database. So here we have the key-value database. That's how you store data in it, but it's not that simple, to be honest. With Redis, for example, as a key-value database. You have other databases that solve different use cases like hash set and list and so on. And MongoDB, you're going to store the data as Python, which is a data structure that MongoDB developed for that database. And the main reason you want to go with non-relational database is you want flexible schema, right? And we're going to talk about when, as you can see right here, when to choose what, right? But here, as you can see, where there is an example, there is no SQL, right? There is no SQL database, so there is no structured query language. They have domain-specific language, and that domain-specific language, it has some SDKs for each programming language, and you're going to use that SDK to query the non-relational database. So here, it's very important question to ask. When to choose what? When I'm going to go with relational database, when I'm going to go with non-relational database. Here we have the start right there, and the most important thing, in my opinion, is your schema is fixed or not. If it's fixed right away, no, this is wrong. I think it's like this. Yes, it's very relational, our database, like bank information or user account information, whatever that is. So go right away to relational database, Postgres, MySQL, and so on. If we don't know like how the schema is going to look like yet, we need flexibility. We just figuring things out, right? We're going to go with what? Non-relational database. And the way you think about it is the data is very structured. Yeah, relational database. It is not structured yet, non-relational database. The second most important thing is consistency, right? Do we need the data to be very, very consistent at all time? Then we're going to choose a relational database. We're going to talk about what is ACD, ACID. It's very important topic in databases. And if not, if it's consistency, we can just trade it off for more availability or more horizontal scaling. Then we don't mind a bit of eventual consistency. And the difference between instance consistency, synchronized consistency, and eventual consistency. In eventual consistency, well, the data at some point in time is going to be consistent, right? If we cannot tolerate that, then we should go right away straight to relational database. If not, we will go with non-relational database. And the third important thing is scaling, right? How you plan to scale our database. Are we going to go with vertical scaling? We're going to use bigger machine whenever we need an upgrade, or we want more of cloud approach, right? We want maybe horizontal scaling, more nodes. We add more nodes when we need them, right? If that's the case, I suggest you go with non-relational database. If you need vertical scaling, on-premises server, big one, you know how much the user, how they're gonna grow, go with vertical scaling, relational database. Now the use cases, that's the fourth. Why? Because those three things, in my opinion, are the most important thing for you to decide. Are you going with relational database or non-relational database, right? And keep in mind, you can migrate, like there is lines in between, right? This is very important. A lot of people forget this. You can migrate, right? And a lot of people start with this route, unfortunately. Most of the beginners go straight ahead to non-relational database, mirror stack, MongoDB. And I'm against that. Why? Because there is so much for you to learn in a relational database. In fact, if you started with a relational database and then transition into non-relational database, you're going to be very, very, very good software engineer from the perspective of databases. Unfortunately, people will go the other route, and they end up really, really hating relational database. I'm not hating on non-relational database. Keep in mind, most of my SaaS currently runs MongoDB for the past 2 years. I'm enjoying it. I love MongoDB. It's been 2 years since I touched SQL query, but I do keep my information fresh, right? I do some exercise and so on. And anytime, like if there is a freelance work or related to SQL database, I don't face challenges. Why? Because I keep information fresh and I keep my X sharp. That's important. My X is very, very sharp. I can cut trees, right? I can cut trees anytime, any day. So here we have described very important thing, and now we jump into the fourth thing, and that fourth thing is use case. Unfortunately, I've seen a lot of experts have this flipped in their mind, right? They talk about the use case before the schema, right? And that's really, really bad, because the way they do that is because okay, you're gonna drive the schema from the use case, yeah, right, but you can do whatever schema you model in relational databases, you can model in non-relational databases, right? And that's why you want to start with the schema, because the schema is going to make your life easier. I'm talking about long run, right? And finally, the use case. So are we building something that need high consistency, and we need transactions, right? And we need ACID and those stuff. We're going to talk about it, explain it next. But do we need that? Are we building a bank, right? A bank system? Are we building user accounts for whatever company? Or are we just building analytics, streaming, schemaless data, unstructured data, big data, right? Real-time data. So if we're doing that, we're going to go with none, right? Here we're going to go with, that's it. I think those 4 things is very important for you to decide where to go, right? And now we're going to talk about something very important. By the way, if you're going to notice that we just headed straight to the route of non-relational database, because that's for me personally, I think they are more complex than non-relational databases. If you have strong fundamental in relational databases, non-relational database is going to be very easy for you to learn on your own. So now we're going to talk about assets. By the way, transaction exists also in non-relational database, but every non-relational database have its own implementation, but some concepts do apply. The first concept is atomicity. I think I said it right. Atomicity. Let's do that. If I ask in an interview, so ACID stands for four things: atomicity, consistency, isolation, and durability. When I'm being asked in an interview to explain ACID, the first property of ACID, I always say atomicity is all or none, and I'm just gonna be quiet. And it's really funny. I just look at the interviewer, and his face says, "Are you challenging me for a duel?" Because this is how I like to facilitate my interviews, right? I'm not doing much recently because I'm very busy, but I do sometimes just to keep my X sharp, as we explained. It's very important, right? You need to be prepared to cut any trees in front of you anytime. So here we said atomicity is all or none. What do you mean by that? Well, in transaction, database transaction, we want our transaction either to all succeed or all fail. So if they all succeed, what are we gonna do? Yes, we're gonna have a new database state after that transaction. If they all fail, what we're gonna do basically, we're gonna roll back to the DB state before. And why that is important, I'm gonna give you an example. Imagine transaction A, I'm just gonna type some stuff here. Imagine it's a bank, right? So balance -1. We're doing some kind of transaction. We're transferring money from bank account A to bank account B. So here in transaction A, bank account A got balance minus 100, right? And then here in transaction B, balance plus 100. Our user, using our banking system, transferred just 100 from account A to account B. So why you want to put this in the transaction? Well, here is the thing. So let's assume we didn't put it in the transaction. And this right here actually failed, right? This right here, this query failed, right? And this query went through. We have a problem here, right? Which is the second thing we're going to talk about, consistency. Always valid state. We entered very invalid state. What's going to happen, basically, it's going to be a race condition, right? If this right here failed, the money is gone. Right? What a banking system is that? What a banking system. The money is gone, it disappeared. No trace for it. And you cannot prove, right? The money is simply gone. The only thing you did, the only log in the system, is you transferred the money. When you go to the bank, your account B, there is no money, nothing, right? And that's why we put all of this inside the transaction, one transaction, right? In that case, they either all commit, right? Or roll back to the previous state. And that's a pro tip. When you do something on a production database, right? Always do it in the transaction. Always do it in the transaction. Why? Because if you mess up something, you just can roll back the transaction, right? And nothing happened. Nothing happened. Nobody gonna see nothing happen. And that's very powerful, right? And that's why autonomicity is very important in transaction, all or none. Remember it like this. All transaction or none of them. The second property is consistency. It's related to the autonomicity example up there. So here we must adhere to the database that we're using. Its rules, its constraints and principles, right? And if we did, what is going to happen, we're going to have a predictable state. And whatever we do is going to turn into valid database. If we didn't adhere, for example, to autonomicity property, we're going to have invalid state, as you explained in the bank example, right? And that invalid state is not feasible. That's why it's very dangerous, right? Banks went, companies, businesses went bankrupt because of bad query. I'm 100% serious. I'm not, saying rumors or theories. This happens. A lot of companies went bankrupt because of a simple race condition. So that is very important for you to adhere to the database rules and constraints. Why? Because of consistency. We want the database always to be in a valid state, right? And the moment you break a rule, the moment you break a constraint, what's going to happen? Always, right? You're not special. You're not that special. With databases, right? Database is not like gym membership. You go obtain and then go right there. You have no result, right? No result. You just exist there, right? No. With databases is unforgivable. Just for you sitting doing nothing is unforgivable. So yeah. So here the predictable state is valid state always when you adhere to the rules. If not, we're going to enter what invalid state. And we explained in the bank account example up there. And that's what is consistency. Consistency what? The second letter of ACID, always valid state. So now we got into very tricky topic, right? I just simplify it for you because this topic is complex. There is so many levels of isolation, right? But I'm just trying to give you the clue, right? And that clue with oscillation, always think no data reads. What do we mean by data reads? So here we have two transactions, right? The first transaction writes, the second transaction reads. What's going to happen is that transaction A committed the data, right? And changed the data into new data. but we're running concurrently another transaction, and that transaction is P, and that transaction reads data. Unfortunately, a race condition happened, and we're reading the old data, and we're doing something with it. Oh, that's a dirty read. And that's how you remember it. So the way we fix this is simple, right? What we're gonna put our read query or our write query, or both of them. We're gonna put them in the proper isolation level. And I'm not gonna explain isolation levels. I'm gonna encourage you to go ahead and read about them, right? They're very simple. And yeah, read, for example, Postgres. Right, type in Google Postgres isolation levels. The first layer, we're talking about the explaining the concept so you understand. And for implementation, always go back to the documentation. Even if you know, go back to the documentation, because you're gonna forget stuff. The human mind is only, I think, one study says 1 gigabyte of storage, right? And when you stuff new information there, all the information is gone, right? And you need to keep the most important information fresh in your mind always. So now durabilities. Durabilities in the transaction, ACID transaction, is very important. So when we create a transaction that writes something to the database, or writes something to the database and commit it, what we want to do, what we want basically, if a crash happened, if the database server crash happened, there is some snapshot of the state somewhere in the database system, right? And that snapshot, what it's going to do basically, that it's guaranteed for us is that transaction is going to be committed after something, on restart, on whatever. It's guaranteed to us, right? In the database design. Great. And that's the most important thing about consistency. When you do something wrong in the database, it's not the database. You don't need to say, okay, I'm done with Postgres, right? I need to go to MongoDB, just MongoDB. I'm not doing relation database anymore. You most likely, even MongoDB, you can do a lot of mistakes, right? Because they're different models, right? Always adhere to the database rules and constraints. How you do that? You need to read the documentation of the database that you're using. And squeezing all the documentation in this video is going to be time consuming. We're not going to do that. So the second thing we're going to talk about is a very important topic in databases, and that topic is normalization. When you design a schema in any database, to be honest, not only relation database, even MongoDB has its own version of normalization. So here what we're going to do basically is the process of structuring relational database accordance with series of so-called normal factors in order, right, to reduce data redundancy and improve data integrity. So what are you aiming for is two things: redundancy and improve data integrity. And how you do that? Well, some very smart people designed something called normalization factors, and each for the normalization factors, indeed it's only for the relational database, I think. Because in MongoDB, normalization is a different story, right? They have their own they invented their own type of normalization. And now we understand what is normalization. It's factors, right? Levels. Each factor take you to the next thing. We have a really nice table from MongoDB we're going to see. And why are we doing that? We do two things: data redundancy, we want to reduce that, and we want to improve our data integrity. So why we normalize, right? We already answered that, but actually, there is like something you want, right? What you want is reducing data integrity, data redundancy, and the second thing you want is what? Is data integrity, right? High data integrity. You want high data consistency with your database. But now, why you should do it, right? What's threatening you if you didn't do it? Right? What you desire is reducing data redundancy and integrity. That's what you desire. But what's threatening you if you didn't? Side effects. Side effects in the relational database always, not only in relational database, even in non-relational database like MongoDB. If you didn't normalize your schema well, you're going to have side effects, and that side effect is going to be unpredictable. Let me give you some example, right? So in MongoDB, it doesn't have a table, it's a document, JSON document. And one of the great features in MongoDB is embeddable, right? You're going to embed a schema of different entity inside an entity, right? So imagine with me if you updated that entity with the embeddable, right? How are you going to handle that embeddable within your JSON schema? You see, software is all about trade-offs. Yeah, it's really nice to have the data in one place, right? But also when the user not update this embeddable that entity that has embeddable, no. What if the user updated the entity itself, right? The entity itself somewhere else with a form or something. What are you going to do with the embeddable right here? You see, you must guarantee to your users that. Believe me, I've seen people professionally get bamboozled when I say that, right? How are you going to handle this? It's very important for you to handle this. This is a very important edge case, right? When user update the embeddable, are the entity right here is going to get updated, yes or not? Because MongoDB by design doesn't handle that for you. So what are you going to do? Are you going to insert, instead of inserting the embeddable, you're going to insert the ID, right? Well, that's against MongoDB rules. Not totally against it, depends, right? If you're expecting that data to grow very large, or there is 10 megabyte limit on a single document, so you better off inserting the ID there, creating a reference. If the data is small, yeah, you have it there. But also, you need to think about the updates, right? And it was a bit long, but it's very important for you to understand. And that's the anomalies that we need to normalize for. And that's the side effects that lead to unpredictable state. Here we have an unpredictable state, right? Two edge cases, right? We either, when we update this embeddable, the entity that has embeddable in it in MongoDB, we need also to update that entity that we embedded, or the other side around. If we updated the embeddable, we need to update it in that entity, right? And here we have some anomalies. Let's just start discuss it. So here insertion, now we're going to go back to SQL. As I told you, it's more focused, but I wanted to give you an example here, right? So you can generalize this. So insertion anomaly, basically, we cannot be recorded for all. What do you mean by that? You have a table right here, right? As you can see, we have inserted a new faculty within our university or school, whatever that is. And he doesn't have any when it's logical, right? When Dr. Newsom joined our university, he's newly hired, right? He doesn't have courses yet. So how are we going to handle that? Is it okay for us to put null there, right? Are we going to put different value, binding, or what are we going to put there? Why this is very important? Because that's going to lead into unpredictable state, right? Not only in the database, but also in the backend, like null pointers and so on. And also in the front end, how are we going to display that? No courses assigned and so on. And the second thing is the update anomaly. We just discussed it with the MongoDB example. Let's just discuss it here. It's the same exact example, but simplified, right? So here we have the update anomaly. Same thing, expressed in what? In multiple rows. In MongoDB, same thing expressed in different entities. Here, the same thing is expressed in multiple rows. Why this is problematic? Well, so when we update the address of our employee 519, which one are we going to update? Are we going to update the first one, or are we going to update the second one? You see, very inconsistent, very consistent, unpredictable state. Why we reach this in the first place? Because we didn't normalize our data model. So here our table, we didn't normalize our table. So here we have another third one example, deletion anomaly, right? So you always need to think about the deletion anomaly as follows. When you delete something, you're deleting a fact. So make sure you are indeed wanting to delete the fact you want to delete. Why this is very important? Well, imagine if we wanted to delete the course assignment of English 26, how are we going to handle this? We can do a mistake, delete the whole faculty member because we didn't normalize our data, just to delete this. And that's very problematic. Why? Because it's very unpredictable state, right, in our database. So how to avoid all of that? How to avoid all of these three, insertion anomaly, update anomaly, and delete anomaly? Well, we need to normalize our tables. We need to normalize our schema, whatever that schema is, in relational database or non-relational database. But here, the normalization factor is for relational database, right? So before we jump into normalization factor, again, why we want to do the normalization? We want to eliminate data redundancy or reduce it. We want to ensure data consistency. We want to simplify the data management, right? Because as you can see, these tables are horrible. It's really hard to maintain. And not really horrible, but it's really hard to maintain, right? Really hard to write query for. And finally, we want to improve our database design, right? So how are you going to do normalization factor? We have this huge table copied and pasted from Wikipedia. Wikipedia is a valid source, by the way. And yeah, I reviewed this table. It looks good to me. If there is a mistake, please let me know in the comments. So here we have all the normalization factors that you want to go every table you design in a relation database. You need to go over them, my friend. Right? You need to go over them. Otherwise, in the long run, you're gonna not make your life easy, hard. You're gonna make the life of other people very hard, right? So be a person that not only make life easy for him, make life easy for other people, right? Through putting thought, putting their soul into the work because they love it, right? And here, what we're gonna do basically is we're gonna talk about normalization factor. Here we have unnormalized, right? Unnormalized factor is the first factor invented, and here in unnormalized factor we have unique rows and no duplication, right? All of them basically have this, all the factor, because it's like it's steps, right? Steps. Not all of them have everything, but steps, right? And here in the second normalization factor, as you can see right here, scalar columns. Columns cannot contain relational or composed values, right? Here what we mean basically, this column right here, course, cannot have two pieces of facts, or fields in one field, right? And we also, with the field here, right, the column, should not have a relation. If you want to make a relation in the relation database, you use primary keys and foreign keys, one-to-one relationship, one-to-many relationship, many-to-many relationship, and so on. And that's the whole table. I highly recommend for you to read about normalization factor. We just given an introduction for it, right? And there is so many levels you can go through, right? And finally, here we have ORMs, right? And ORMs is for you as a developer is how to say the thing is going to make your life easier, right? Because you're not writing so much SQL query, which you should know how to write. It's a must. It's not negotiable. It's not like now I'm just going to use an ORM. If you want to know what you're doing, you should learn SQL and then go into our ORMs, right? Always develop with ORMs, for sure, 100%. Most of frameworks out there nowadays have ORMs, but also understand the underlying, right? Because the software, as we described in this series, understanding the system series, is layers and layers and layers and layers of abstraction. Great. So here what do we have? What is exactly object relational mapping? Well, here we have a developer is going to write user find all, right? And this method, the ORM is going to parse a query and create a query, and it's going to generate an SQL, select everything from user, right? And select everything of your user is very horrible, right? Imagine if you have hundreds of thousands of users, and you just, from that query, you need one user, right? So here where comes the knowledge of SQL, structured query language, comes in. Because here where you're going to say, no, find all, it's bad. I don't want to find all. I want to add a filtering. I want to add where user, IDs, blah, 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 right? Great. So that's what it's going to do is, of course, before everything, ORM is going to do, it's going to create migration for the user table, and you, as a developer, is going to create the schema for that table using the ORM. But the main task of the ORM is its name, object creation and mapping. It's going to take tables and turn them into an object within your programming language. Great. So here we have a very important issue that a lot of developers fall into without noticing when they're using ORMs. Here we have an example for our ORM in JS, and that problem is N+1 problem. What is this problem and how to explain it? Well, imagine this. What if you need to run a specific query multiple times? How are you going to do that? Most developers, what they're going to do, without them noticing, it's just simple logic. I'm going to have a for loop, within inside the for loop, I'm going to have that query, right? And that's really bad. Why? Because what you wanted to do here is just, you requested the list of posts with authors. And you query all the posts, that's the one query. Return the post, what you're going to do right now, you're going to create a loop, right? Within the loop right here, without you noticing, the ORM was going to do is going to query the author by post author ID in queries and return the author. So in the background, for you as a developer, when you use the ORM, you see one query, but what happened, one query and some for loop logic. But what happened, right, in the background there is done 10 queries, additional queries. And that's really bad, right? We talk about scalability and performance. And how to catch that? Well, every ORM, every framework have its own profiling and analysis tool. And after ORM, we jump into a very important topic, and that topic is caching. So why you use caching? Well, databases read from disk, right? Disk is a bit slow. When the program reads from memory, it's a bit faster. We're talking about nano, I think, seconds or microseconds. And we want that speed for certain things. What those certain things? Well, the things that our users request more frequently. Think about currency, right, and financial system. Is it reasonable for us to put all the currencies within our front end? If we have so much money and someone else paying our bills, and we're not watching so much for profit and cost, profit margin and so on, yeah, no one cares. But if we do, like if we are a startup that working to be profitable and successful, this is too much cost. We're talking about gigabits of not terabits per second, depending on our traffic. We put all the currencies, right, and then in the front end, and the bill counter is gonna count. Cloud provider is gonna love you, right? They're gonna welcome you. They're gonna have so much money from your stupidity, right? No offense to you, but this happened. I've seen that professionally, right? I'm doing that actually. I'm doing that in one of my startup. Why? Because there is not much traffic. It's low traffic. I know it's gonna stay low traffic because I'm not gonna market it, right? But unfortunately, I've seen professionally some let's say client-facing applications that have hundreds of thousands of users, they do this stuff. So what do you want to do here? We're going to make this fast and efficient. How are we going to do it? We're going to put this piece of data in a cache. Right? We're going to use Redis for it. Whenever the user needs it, it's going to request it from that cache, not from the database. Why is that? Because it's accessed frequently, and it's not very big, right? How many currencies in the world, right? It's a quantifiable number, right? And yeah, that's the main reason we want to use cache. And we have CDN, Content Delivery Network, right? Caching for front end. So what we're gonna do basically here in the CDN, we're gonna request client request. We're gonna see if we have it in memory cache Redis or memcache. If it missed, we're gonna hit the application server, right? If we have it here in our CDN, we're gonna return it to the user. And CDN, the way you think about it, is multiple users, multiple servers across the world that have your front end or server data near to the user, mostly front end or some data near to the user, right? And they use caching for all of that. And there is strategy for caching, right, in the backend. The first one is write back. So the client write data, send request to the backend. The first thing is what you're gonna do, the client's gonna write to the cache, and then we're gonna async write to the database, right? We're gonna do that concurrently, fire and forget. Why are we doing this? Because the data kept, the cache data kept up to date within the cache, right? Great. So and there is much more into it, like how you're gonna handle for errors, retries, and so on. But there is some strategies here. And the second one is write around, and the third one is write through and read through, right? And they all have their benefits and trade-offs when to use what, and I encourage you to read about that. So here we have the scaling of databases, and we have two types, no third. You either go vertical, there is no half and half, right? Actually, some databases are designed for vertical scaling, like Postgres is mostly vertical scaling, and MySQL. And there is databases designed for horizontal scaling with sharding and so on, like MongoDB. So with the vertical scaling, what you want to do basically, when you have more traffic, you're going to go to a bigger, more powerful machine. With horizontal scaling, well, you're just going to add more replicas, more machines to that database cluster, right? Great. And now for scalability and performance, you have very important topic. That topic is indices, right? Always think about indices in this way. They are data structures, right? And their goal is very simple, straightforward. All of them is to speed up reads. And when you do speed up reads, what's going to happen? You're going to slow down writes. Why are you going to slow down writes? Well, because there's going to be an index there on disk somewhere, right? And when you write to the database when you write to the record that the table that have an index on it, what's going to have to be done is basically both things. You're going to write to the table, and also that index need to be updated. And that's why indexes always speed up read queries but slow down writes. How they do that? How they do speed up queries? Well, as we said, they use very, very efficient data structures. And here we have two of them. We have hash indexing, right? And hash indexing is perfect when you're designing a database, which most software engineers not gonna do, and they don't have reason to do it, right? Because there is very, very efficient databases out there. There is some rare cases where there is put your money where your mouth is, right? We have companies that create their own database for a specific use case, but for most software engineers, for 99% of the companies, they don't need to create their own databases, right? They have great databases out there, battle tested, and we should just use them. And here we have so many indexes, so many implementation of indexes for different databases. But two famous indices, we have hash indexing, and here what we're going to do, we're going to have a hash function, right? And we're going to take that information, right, that field that we index in, and we're going to turn it into hash, right? And when we search for that row using that value, right, what's going to happen is basically that hashing function, we're going to use it, that we're going to use it again for equality matching, right? So hash indexing is great for what? Equality searching or equality indexing of data. But B-tree is a bit different. B-tree is more complex data structure. And the reason it's more complex because it allows us for range query, right? Oh, and here what you can see, we have three main data, right? And we have the root node, and we have the intermediate nodes, and between them, and finally below them, we have the leaf node. For example, if you looked at here, we have F and we have S, right? And on the right we have S, P, and W. And you can see right here is W, Wah, Winter, Wong, and then on the left, I don't know how to pronounce the name, but you get the idea. When we search, for example, for Wah, we're going to go over this B-tree index and traverse it, right? Traverse this tree and arrive at where? Arrive at here, right? And the reason the B-tree got invented is because we want to create a range query. What do we mean by range query? We don't want to only index for search only for a name, for example here John Smith. We want to search maybe for a name of that start with the W of 3 letters and so on. And B-trees and hash indexes are very complicated topics, and we're going to have it somewhere in the understanding the system data structure or whatever that is. We're going to have a video on them, but for the length of this video I think it's already past the 50 minutes. What we're going to do, we're going to skip that for now. Now finally, I think the most important thing for you to understand when it comes with databases and any system out there is CAP theorem. I think we explained CAP theorem, if I'm not wrong. Basically what you want to think about it when you work with databases is you can only choose two of three. Two of three what? Partition or availability or consistency, right? So if you're aiming for very high availability, 99% of availability, right? So what are you gonna do? Basically, you need you're gonna do two nodes of, for example, Postgres, right? And when you do two nodes of Postgres, how are you gonna synchronize them, right? Right? Are they gonna be synchronous, or are you gonna say to yourself, here why are we doing two nodes? Because we're aiming for high availability. Here we're gonna have active, passive, or hot, cold, right? When this failed, this is gonna take over primary, secondary, and they have their names, right? Here we're gonna have a VIP, virtual private network, and the traffic is gonna be routed through this virtual IP network, right? And that virtual IP need to be highly available as well when we're designing a highly available system. And here we have our two databases, right? Two nodes of databases. And what's going to happen here when we aim for very, very high availability, we're going to run into a problem, right? We either going to choose partition terminals, right? Right here in our replication methodology, or we're going to say no, we want consistency over that. If you want consistency, right, very, very high consistency, like we're talking about banking or something very, very sensitive, then the replication needs to be synchronized, right? You cannot have passive active. Both of them need to be active, right? And that's very expensive. That's very expensive to do, right? Because you're not gonna have one server, you're gonna have two servers. And I'm not talking about any server, right? We're talking about very, very big servers, like IBM servers or something like that. And if not the case, we can tolerate a bit of consistency. We don't mind eventual consistency, right? We're not creating a banking system. We're okay, like for a split of a second or for a few seconds, data here in this node is not the same on data in this node, but the data is eventually is going to be what? Consistent. That's what's called eventual consistency. Then we're going to say, okay, what are we going to do? We're going to, in that case, what we're going to do is just we're going to create more nodes right here, right? We're going to do replication, relaxed replication, and aim for partition tolerance, and our consistency model is going to be what? Eventual consistency, relaxed, right? And that's the CAP theorem. Your C is consistency, A is availability, and Z is partition tolerance. You only can pick 2 out of the 3. So that's the whole video of the database. It was a bit long, but I think the information is very valuable. And yeah, thank you for watching. More to come. And this video, as you saw, is just very, very raw, and a lot of information in it. Take it slowly. You don't need to watch it. If you watch it, watched everything, good for you. If you took it in the bath, that's okay, right? And yeah, so for the next video, see you inshallah in the next video.